In the previous video, we went through a couple of important topics. Actually three. Two topics and an application. Topic number one, the concept of the definite integral using the idea of the signed area. Here is a visualization. The positive part, the negative part, adding them all up, we have a signed area, which we call the definite integral and represent kind of like this. Easy understanding, coming from easy visualization. Great, but then again, how am I going to calculate this thing? That's the difficulty related to the definite integral if you use this path. So here comes the fundamental theorem of calculus, and that allows us to calculate the definite integral using the antiderivative formulae. If my function small f is a continuous function defined on a closed and bounded interval a to b, and the definite integral a to b f of x dx can be calculated through its antiderivative function capital F. Capital F of b minus capital F of a, plugging the top, plugging the bottom, subtracting one from the other. We went through some example problems, applications. Let's take this one for example. How to calculate this definite integral? First, we manipulate the integrand, kind of like anti-differentiation problem. After completing this, we can calculate the antiderivatives using antiderivative formulae, and then the fundamental theorem kicks in. Plug in the b value, plug in the a value, subtract one from the other, and we have the answer. And shorthand for that is this bracket notation. Now let's continue on to this definite integral, and let's answer this question. This one is actually a trick question, to tell the truth, because if you try to calculate this antiderivative of this thing, man, that's not going to be possible. And in some cases, instructors write a problem that can be calculated, but student have to pay the price, and then student actually do fall into that trap and then indeed pay the price. Actually, this kind of problem is better because it is very clear that antiderivative computation for this is impossible. So what do? Please note the following. The integrand is an odd function, and then this integral is going from -2 to 2. So we must have the symmetry with respect to the origin, and we'll have a cancellation. This is the actual graph, positive part and negative part canceling each other. So the antiderivative, or actually, excuse me, so the integral is 0, even though antiderivative is impossible to find out directly. Another example here, again, instead of trying to find out the antiderivative, which is going to be very difficult, we use geometry. What is the square root of 4 minus x squared? Actually, it's a circle. Circles of radius 2 centered at the origin. This is square root of a squared minus x squared form. Alright, and then what do we have? We have this semicircle from -2 to 2. So the area formula of a circle is pi r squared, but we need 1/2 for that because this is a semicircle. Calculating, we have an answer, 2 pi. Okay, those were easy. This one is far more significant. This one is easy too, but it's significant. I've seen far too many students doing something like this. Kind of answering like this. Oops. So absolute value, kind of like this. Integral of an absolute value is the same as absolute value of the integral. Actually, this is wrong. This is not right. In order to make it right, you have to change this equality into an inequality. The left hand side is a little bit bigger, and sometimes they're the same, and in those cases typically f is positive throughout or negative throughout. so that absolute values actually do not matter too much. If f goes up and down, in that case, here in this integral we'll have cancellation, positive part, negative part cancelling out, kind of like the previous problem. Here no cancellation because everything is positive. So these two are fundamentally different integrals. So how do we handle that? We're going to divide the interval in appropriate place, and appropriate place is pi. Because between 0 and pi, sine of x is positive, so absolute value of sine of x is just sine. Between pi and 3 pi over 2, absolute value of sine is negative sine of x because sine of x is originally negative, so putting extra negative sign will make it positive. Once we have the second line, everything is now easy. Antiderivative of sine is negative cosine, antiderivative of negative sine is cosine. Apply the fundamental theorem, plug in a b value, plug in an a value, subtract one from the other. Remember the cosine of pi is negative 1, so negative, negative, positive, and so on and so forth, and we have an answer. If you calculate the integral without the absolute value, you're going to get different answer. Here's a visualization. Light blue dotted curve is just sine function going up and then down. As you can see, this negative part will cancel out a part of this positive part. The red solid line is absolute value. There is no cancellation for the red part. Sorry. So everything is positive. Consequently, the red integral is going to be bigger. Naturally, 3 is bigger than 1. Even if I give you different functions with absolute value, the idea is the same. You have to find out the crossing points, and then that's where you divide the integrals. As a matter of fact, we have application properties of integral. Yeah, this one. And then from a to b f of x dx, from b to c f of x dx versus a to c f of x dx, I visualize kind of like this. Brown integral plus purple integral turns out to be the total. But this is poor way to separate. The most strategic choice will be right here, so that you can actually do some computation. Okay, so much for definite integral computation problems. Now let's focus upon another aspect of the fundamental theorem of calculus, that is taking the derivative of an integral. Here's a corollary. If I define a function g of x using a integral like this, from a to x f of t dt, then the derivative of g is the same as the original function that we started off with. The reason? The fundamental theorem of calculus says that definite integral is more or less an antiderivative. So basically what you did is to take a derivative of an antiderivative. No wonder you get the same function back. The only thing you have to be a little bit careful about is the character. We started with x. So in the end, we have to finish with the same character. This dummy variable t, or whether it is given by s or u or y, it doesn't matter. It just goes away. Of course, if this main variable had been given as not x but as something else, y or z or anything else, you have to use that one. But this is not the most useful form. This one is. And this one combines the fundamental theorem of calculus and the chain rule put together, and basically number 1 and number 2 topics put together in the same problem. So this is an important example, and we're going to go through some examples of these later. And let's talk about the proof. Let's begin with this one, and then by fundamental theorem of calculus, this is what we're going to get. What did I do from this fundamental theorem? I just changed a and b to a of x and b of x, and then x is already taken, so this dummy variable is now changed to t. That's all I did. Of course, this capital F is antiderivative, So I didn't change anything. Now we take the derivative of the left-hand side. So I took the derivative of the left-hand side, so I'd better take the derivative of the right-hand side too. So how do I take the derivative of this composite function? We have to use a chain rule. Number one, derivative of the outer function. Number two, inside stays the same. Number three, we have to multiply the derivative of the inside. Let's do it again here. Chain rule number one, derivative of the outer function. Number two, inside stays the same. Number three, we multiply the derivative of the inside. There goes the chain rule and the fundamental theorem of calculus. Final observation is that this capital F prime is actually just f, small f, because that's the way this capital F function was defined, as an antiderivative. Now let's move on to applications to these. Here are some problems. I'm calculating the given derivative. Well, let's see. Here are three problems. Looks like the third one is the hardest, and the other problems, this one and that one, actually follow immediately from this corollary, as a matter of fact. Or also, you can simply use this formula and remember that 2 is constant, so derivative of 2 is 0, so it goes away. 1 is constant, so derivative of 1 is, so it's 0, goes away. Just remember that thing, and then you can use this formula to these problems too. Let's move on to the third one, and then, okay, let's just copy this, and then let's go ahead. This formula says all you have to do is replace t by the top and bottom, so it's gonna be the sine of that thing minus sine of that thing, and then in place of t I have to replace that by x squared plus 2x. Okay, and then I have to replace this x squared plus 2x in place of t downstairs as well, and so plugging in is complete. F of b of x is done. All I have to do is multiply the derivative of the inside. What is the derivative of x squared plus 2x? It's customary to multiply the simpler factor in the left hand side, so I multiplied b prime of x in the left hand side. So that concludes this one. Let's move on to the next one. A of x is 2x minus 1, so that's what I have to plug in place of that t, both numerator and denominator. I'm not done yet. I have to multiply by a prime by the chain rule. So what is the derivative of 2x minus 1? That's just 2. So here goes the derivative of an integral. Well, we have a little of time left, so let's move on to this problem here. And if I use this same argument here, and then here I'm replacing all this by x and x, and then I have to multiply the derivative of x, which is 1. So 1 times that. And how about this top? I have to replace all this u by 2. Not that I'm gonna actually do that, but you have to multiply the derivative of 2. That's a constant, so that's multiplying by 0. So experienced students will not do this at all. Oh, this is constant, so I'm just gonna ignore that part because that's 0 anyway. And then just work out the the bottom part, and the negative 1 times minus, not negative 1, minus came from the fundamental theorem. 1 is the derivative, and then just plugging in x, and that's why we get the answer. This problem can be done the same fashion, notably easier.